Right, so let's take this equation and let's multiply it with d straight through. Okay, so what is that equation going to become if I multiply it through with d? So it is going to be basically AD plus BD times D. Okay, and what I'm going to do is the second equation, which is that one there, I'm going to multiply that with B. Okay, so multiplying that with B, I get B there, I get B there, and I get B there, and if I multiply B with 0, I get 0. Okay, so so those are two equations, and I can go and basically cancel this term with that term. Okay, so basically that becomes, so labeling them 1 and 2 respectively, if I take 1 and from 1 I subtract 2, then I basically get AD minus BC times x1 is equal to D. And from that, remember we said that this term AD minus BC, back there, AD minus BC is non-zero. Basically go and solve, I can basically go and solve for x1 as D divided by this non-zero term, which is AD minus BC. Okay, so I'm allowed to do that. Okay, so I've solved my first variable x1. Now moving on, we want to solve for x2. And for x2, we're going to use that part there. Okay, let's move my first variable that I solved that side there. And let's move on to my next set of equations. I know I talked about x2. Let's rather solve x4. So what I'm going to do is I'm going to take the first equation. I'm going to multiply through by c the first equation, right? So let's see what that looks like. So if I multiply through with c there, I get c there, and I get c there. Okay. Then the second equation I'm going to multiply through by a. So let's take the second equation and let's multiply through by a. So that is going to be a, and we're going to get a there, and we're going to get a there. Okay, then what I'm going to do is I'm going to label that as my equation 1 and that as my equation 2, and then taking from 1 and subtracting 2, we are going to get that is going to cancel with that, and we're going to get that CB minus AD times x4 is minus A. Now again, basically from that expression there, we can go and do what? Now if you guys go back, that AD minus BC is not 0. So AD minus BC is not 0, so therefore CB minus AD is not 0. So you can basically go and solve for x4. You can basically go and solve You can solve for x4 as minus a divided by that term there. Okay. And basically then, if we just write that differently, we can make that sign a positive sign, and we can basically switch the two around like that. And we can just write a minus there. Okay, so therefore, again, we have solved for x4. So there we have solved our second variable. Now we just have 2 to solve, and that we get from the other equation. We need to solve x2 and x3. So from the first batch, I need to solve x2 and x3. So I want to cancel the x1s. So I'm going to do that by basically multiplying through by b, the first equation. So I'm going to multiply through by b, and that I'm going to get b there, and then I get b there. Then I'm going to take the second equation and I'm going to multiply through by a. There we go. Multiply through by a, and I'm going to multiply through by a. And so basically what I'm going to do is again label that my first equation and label that my second equation. And then what I'm going to do is I'm going to take from 1 and I'm going to subtract 2. Okay. So what I'm going to be left with is BC minus DA times x2 is equal to B. And so we said that A times D minus B times C is not 0. So therefore BC minus DA is not 0. So I can then again solve for x2 as basically minus B AD minus BC. Right, so there I have solved my second last variable, and I'm going to move that again to the left hand side. And then lastly I need to solve x3. So I'm going to multiply this equation, first equation, I'm going to multiply that with d. Okay, so multiplying through with d, I get this. I get this, and on the right hand side I get 0. And then the second equation I'm going to multiply through with c. So let's see what happens. What I get there. I'm going to multiply. It with c. So that's going to become c, and there is going to become c. Okay, and on the right hand side we've got c. Okay, so again I'm going to label that my first equation, that my second equation, and then it's going to be the same story. What I'm going to do is I'm going to, from that information, I'm going to then take I'm going to take 1, and from 1 I'm going to subtract 2, and basically that is going to lead to AD minus BC x3 is equal to minus C. And again, because AD minus BC is a non-zero number, I can go and solve for x3 as minus c divided by this non-zero term, which I can cancel on the left. Because it's a non-zero term, I can do that cancellation. Okay, so basically, what is the moral of the story here? We have solved all our variables. So let's see what our matrix looks like. Right, so we have B equal to that. So here's my x1 term. So there's my x1 term. There's my x2 term. There is my x3 term. Here's my x3 term. And lastly, my x4 term is that. Okay. Right. So simplifying, we get, right, so that matrix can actually be written as, take that term out, and what we basically do is we delete that, we delete that, and we delete that. So that is my inverse of A. Okay, so that brings us to Theorem 5. If you have a matrix A and it's invertible if and only if AD minus BC is not 0, in which case the inverse is given by that there. And AD is that term multiplied by that term minus that term multiplied by that term. And this AD minus BC is called the determinant. It's called the determinant of the 2 by 2 matrix A, and therefore the invertibility of a 2 by 2 matrix is determined by whether the determinant is 0 or not. If it is 0, the matrix determinant is invertible. If not, it is not invertible. Okay, so perhaps it's just appropriate for me to mention something about this result here, which states that a 2 by 2 matrix is invertible if and only if the determinant of A is not 0. Alright, so that statement there, how do we prove it? This is an if and only if statement. So we need to prove prove an if and only if statement. What an if and only if statement, what it means is that you cannot have one statement without the other. In other words, if the statement on the left is true, then the statement on the right will be true. And likewise, if the statement on the right is true, then that will imply the statement on the left is true. Now, so proving from right to left, what we do there is we assume that the determinant of A is not 0. Then remember what we did. Then we proved previously that A's inverse is going to be 1 over. Okay, we proved that previously, if you guys can remember. So we proved that A is definitely invertible, its inverse exists. And remember, that term is the determinant of A. And if that term is not 0, then we could actually solve the inverse. Right, so now proving from left to right, what we now do is we assume A is invertible. And now we need to prove that the determinant of A is not 0. So we can do this by contradiction. So assume so assume to the contrary that the determinant of A is in fact 0. I recall that because we said A is invertible, we set B equal to that matrix with x1, x2, x3, x4, and A was the matrix A, B, C, D, and remember we said that because A is invertible and B is A's inverse, we said that A times B is equal to B times A is equal to the identity. Okay, and remember we had 4 expressions that we obtained. Right, then remember we solved for, we obtained these expressions, x2 times AD minus BC was B minus B, and we got it from subtracting those equations that we set up, and the equations we got from this matrix equation. Okay, now in this case, we said, if we go back here, we assumed that the determinant of A is 0. Right, so we have that AD minus BC is 0. Okay, so now I'll just take that in mind there. So hence, okay, so AD minus BC is 0. So that's 0, okay? That is 0, okay? I've not divided by 0, or I've not done anything illegal. That's 0, and that's 0. Okay, so what is the implication of that? It implies that C is 0. It implies that A is 0. It implies that B is 0. And it implies that D is 0. Okay, so we've got a problem here. Okay, and so from that, it basically implies that A is equal to B is equal to C is equal to D. These entries are all 0. Okay, so remember we said A times B is equal to B times A is equal to the identity matrix. And what is this A matrix? That A matrix is basically equal to the 0 matrix. The 0 matrix is the matrix where all the entries are 0. Okay, so basically that is going to be the 0 matrix times B times the 0 matrix, okay, and that is the 0 matrix. So on the left hand side I've got a 0 matrix, and on the right hand side I've got the identity matrix. Okay, so this is clearly a problem. Alright, so this is impossible. This is impossible. Hence, the determinant of A can definitely not be 0. Okay, so the determinant of a 2 by 2 is related to whether it is invertible or not. Okay, I just want to say something about Theorem 4 as well. If B and C are both inverses of the matrix A, then B is equal to C. Alright, so again, suppose suppose A is invertible. Alright, and let B and C both be inverses of A. Right, then we know that A times B by definition will be the identity. Okay, and we also know that A times C will also be the identity by the property of inverses. Okay, so that will then imply that A times B will be equal to A times C. Now, A is invertible, so you can basically take this matrix equation that I have there, okay, and what you can do is you can perform an operation. You can multiply the left with A's inverse, okay, and you can multiply the right with A's inverse, maintaining the order. Remember, if I multiply the left-hand side on the far left, I must multiply the right-hand side on the far left, which is exactly what I've done there. So that is going to imply, again, we have the associativity rule at play, and the associativity rule tells me that I can go and switch the brackets, so I can go and group that bracket, and I can take the other bracket and I can go and group it around there. And on the left hand side I can also go, or on the right hand side I mean, I can also go and do that. And that bracket I can move that because the associativity rule holds. And so that is going to be the identity. And so we're going to get that B is equal to C. Right, so the inverse is unique. A matrix, if it's invertible, it can't have more than one inverse. Okay, so it is exactly one inverse. Alright, so next up is an example, just an application of what we just worked out the right, next up we have a few examples where we asked to apply the result that we previously derived that gives us the inverse of an invertible 2 by 2 matrix. So here they ask us find the inverses of the following matrices. So the first matrix, firstly, if we look at the determinant of the first matrix, it's 1 times 4 minus 2 times 3, which is 4 minus 6, which is minus 2, and that's not 0. So therefore that matrix is clearly invertible. So we can go and find its inverse, and its inverse is basically 1 over the determinant, which we worked it out as minus 2. Right, we switch the 2 around, 4 and 1, and we make the 3 a minus 3 and the 2 a minus 2. Okay, and so that is the inverse of this matrix here. Okay. Second one is the determinant is minus 2 times 3 minus 3 times minus 2, which is clearly minus 6 plus 6, which is 0. So the determinant of that matrix is 0, so therefore this matrix here is not, it's definitely not invertible. Remember, a matrix is invertible, 2 by 2 matrix is invertible if and only if its determinant is not 0. Okay, so the last matrix is a 2 by 3. And the inverse, remember we said the inverse of a matrix corresponds only to square matrices, and a 2 by 3 is not a square matrix, so that's clearly not invertible. Okay, it turns out the inverse can help us a little bit solving linear systems. So the next is solutions to linear systems and matrix with matrix inversion. So recall that a linear system can be represented in this form. We said you can write, instead of the augmented matrix, you can write a linear system as basically in the form of a matrix equation, where x is a column vector and b is a column vector, and a times the column vector x. X is the column vector containing all your variables. Okay, and again, if A is invertible, then this matrix equation can easily be solved. And this is where you guys need to be careful with multiplication. Right, so I'm going to multiply on the left-hand side with A's inverse, but I have to maintain order. So if I multiply on the left-hand side with a matrix, if I multiply the left-hand side on the left-hand side, which is there, what I do on the left, I need to do on the right as well. So I also need to multiply that side with A's inverse, but I need to maintain the order. Because I did this on the left-hand side of because I did that on the far left of the left-hand side, I need to do this on the far left of the right-hand side. Okay, so basically, if I multiply a matrix, we know associativity rules hold when it comes to multiplication, so I can play around with the brackets. I can just not switch the order around. Then a matrix multiplied by its inverse is the identity matrix, right? So we get this solution here. And the identity matrix times a column matrix is that column matrix. Okay, so that is the solution. So if A is an invertible matrix, you can quickly go and find the solution to your linear system. So if we look at this linear system here, we can write it in matrix notation. We can write it as 1, 2, 3, 4. Okay, and the column vector signifies my variables, and then so that's my vector x, that is my matrix A, and that is my vector x. And so now all I do to get the solution in this case is I pretty much check the invertibility of A. So A's invertibility is basically guaranteed because its determinant is not 0. So A's inverse is going to be 1 over the determinant, which is 4 minus 6, which is minus 2. We did calculate this, and what we did was we switched 4 and 1 around, and we made the other minus. Okay. So that is the inverse of that matrix. Okay, so from there we can then basically solve. We can solve our system by noting that it will be A's inverse, which we calculated as that matrix, 4 minus 2 minus 3, 1, and you're going to multiply it with the column vector 1 minus 1. Working that out, we get the column vector, and so we can therefore solve x as x is minus 3. We can solve y as plus 2. Okay, so that's a way of solving a linear system provided a linear system of two equations and two unknowns, because that'll give you a 2 by 2 matrix, and then we can easily calculate the determinant and the inverse, provided the matrix can be inverted. Then just something to be aware of, powers of matrices. If we have square matrices, then we define a to the power of 0 as the identity matrix, and we define a squared as just the matrix A multiplied by itself. And pretty much in general, for any positive integer n, we define a to the power of n as just simply multiplying a matrix A with itself n times, just like you did with normal real numbers. And provided that A is invertible, you can then bring in a negative as well in the power. And A's A to the power of negative n is pretty much just the inverse of A that I take, and whatever it is, and I multiply it with itself n times. So it's taking A's inverse and multiplying it with itself n times. Now, if R and S are non-negative integers, then the exponent rules also work for matrices. So if I take A and I multiply it with itself R times, and I take A and I multiply it with itself S times, and I multiply the two matrices together, then it's the same as just multiplying A with itself R plus S times. So that exponent rule also holds for matrices. Then if you take A and you multiply it with itself R times, and you take the resulting matrix and you raise it to the power of S, then that's just the same as taking the matrix A and raising it to the power of R times S. Then that brings us to properties of inverses. If A and B are invertible matrices with the same size, then A times B is invertible, and in fact A times B's inverse can be determined as B's inverse times A's inverse. Now, a product of invertible matrices is always going to be invertible, and the inverse of a product is the product of the inverses in reverse order. Right, now it's very important to take note of what is Theorem 6 assumption. The assumption in Theorem 6 is that both A and B need to be invertible. So this theorem works only if A and B are invertible. Right, so you have to be careful when applying this theorem. You have to be careful in applying this theorem. The reverse part of this theorem is not true. In other words, if A times B is invertible, if you can go and invert A times B, remember you can only write that minus 1 there if this matrix is invertible. And we said that a matrix is not always invertible. However, if the product between two matrices is invertible, it does not imply that A will be invertible or B will be invertible. If A times B is invertible, it doesn't tell you anything about the invertibility of A or the invertibility of B. So you have to be careful with this theorem. The converse is definitely not true. That is that if A times B is invertible, it does not mean that A and B will be invertible matrices. You cannot say anything. However, if both matrices in the product are invertible, then we can go and invert A times B. Right, so if we assume that A and B are invertible, then how do we find the inverse of A times B? Right, so what does an inverse need to be? What does it need to? It needs to do something. It needs to satisfy that equation we talked about. So if I take A times B and I multiply that with B's inverse, A's inverse, Okay, then that is going to be, remember the associativity law when it comes to matrices and products of matrices. It means we can go and switch the brackets around, right? So I can basically go and do that with a bracket there, and I can also go and do that with a bracket, and that is because of the associativity law. So therefore that is the same as, what does that become? If you multiply a matrix with its inverse, you get that you can replace it with the identity matrix. And the identity matrix times any matrix is the matrix itself. So we have A times A's inverse, which is the identity matrix. So, okay, so this matrix satisfies part of the inverse property. I also need to check the other way around. Right, so to establish that that is in fact the inverse of A times B, we need to just check that it holds the other way around as well. So you're going to take the matrix B inverse A inverse, you're going to multiply it on the left hand side with A B. You're going to see what happens there. So basically, remember, and I can write B inverse A inverse here because I'm given that A and B are invertible, so I can write that minus sign there. You're not allowed to write any minus sign unless you know that A is invertible. So here is associativity again. You can switch those brackets. So there you can group them together there. So that is going to be then obviously, if you go and work that out, again, what is a matrix multiplied with its inverse? It's always the identity matrix. So it's going to be the identity, and that is just B's inverse, which is the identity, B inverse times B. Okay, so basically we can then basically say that hence A times B is invertible, and we can calculate its inverse directly, and we can basically say that A times B's inverse is in fact B's inverse A's inverse. Right, so Theorem 7, again, if A is invertible and N is a non-negative integer, then A's inverse is also an invertible matrix. And it's A's inverse, the inverse of A's inverse is going to be A. Right, that makes perfect sense because, again, if I take A and I multiply A with its inverse, it's the identity, and vice versa. If I take A's inverse with A, that's also the identity. Okay, so what is A's inverse? This is inverse. It is this matrix here, because if I multiply this matrix on the left and on the right with this matrix, I get the identity. So that makes perfect sense. The inverse of a matrix is invertible. And also if you raise a matrix to a power n, then the inverse of that nth power is just basically the matrix A to the power of negative n. And you can also check that that is the case. If you take the matrix A n and you multiply it with this expression, that you can write then as A times A. You do it n times, and there you multiply A's inverse with itself n times. And now it's again associativity that you're applying, so you group those terms together, and that becomes the identity matrix, and you keep pairing them off like that until you get to the very end. That's going to be the identity. And you can also work it the other way around. You can take A's inverse to the power of n, you can multiply it with an, and you get the same result. So it is obvious that the inverse of a to the power of n is a's inverse to the power of n. And then the last property there, the scalar multiple of an invertible matrix Ka is also going to be invertible, and the inverse of that matrix is going to be a's inverse times the scalar that you invert as well. Okay, and that you can also see why that's true. If you take if you take a Ka, then we want to ask, what is the matrix that I have to multiply with Ka to give me the identity matrix? Now, if you take 1 over K's A's inverse, remember the scalar multiplication laws for matrices. You can play around with the scalars, you can rotate them. It's not going to be a problem. It's just the order of the matrices that you have to be careful with. So that's 1, and that is the identity matrix. And then you can also do it the other way around, which you must always check that. So if you do that with Ka, you're also going to get the identity matrix. Okay, so it is clear that those 3 properties hold. Okay, just looking at these 2 examples here, they ask me to quickly calculate a squared. That isn't difficult, it's just the matrix A multiplied with itself, and we already know how to do this. So that will then just be, so we'll calculate that the normal way. And then what is A's a to the power of minus 2, right? So what you're first going to do is you are going to calculate A's inverse. Okay, the determinant of A is 1. It's 2 times 1 minus 1, which is 1. And then basically you switch the 1 and the 2 around, and you make the other entries negative. So that is the inverse. Okay, and then A minus 2 is pretty much going to be, it's the inverse of A squared. Right, so squaring that matrix, straightforward process. Again, you are going to square that matrix, multiply it with itself, and again that is 1 minus 1 minus 1, 2, and then multiplying that out is again another 2 by 2 matrix. Right, so there we've got A minus 2. Right, next they ask us to find A to the power of n, where A is the matrix 1, 0, minus 1, 1. Right, so taking that matrix and squaring it, let's just get an idea of how this works. Right, so squaring this matrix, that is going to be, okay. Right, so looking at A cubed, we see that it will be 1, 0, minus 2, 1, and we're going to multiply that with 1, 0, minus 1, 1. And so that is going to be, right, so you can see there that that entry there seems to always correspond, at least in the first few cases, to that power. So you can just prove this by induction, that the nth power of A is just the matrix on the right hand side. So proof will be Right, so if n is 2, then we worked A squared out as 1, 0, minus 2, 1. And so the result holds. Right, so we can just assume the result is true for n equals k, where k is bigger than or equal to 2. So if we take the matrix a to the power of k plus 1, that is going to be equal to a to the power of k times a. And a to the power of k, we said that by our induction assumption, okay, we have that, and we said that a is 1, 0, minus 1, 1. So that is just going to be the matrix 1, 0, minus k plus 1, and 1. And right, so by induction it follows that in general it's true. Okay, so by induction our claim is verified. Right, just one point, matrix polynomials. In this case, if A is an n by n square matrix, then for any polynomial px, a0, a1x up until amxm, we just define the n by n matrix P of A to be the polynomial where now your variables that used to be these x's are in fact now n by n matrices. So then again the normal matrix multiplication laws and exponent laws are applied here, and basically these coefficients are scalars, and what you multiply the scalars with are in fact matrices. These are all matrices. Okay, so that is just something that you guys need to be aware of in case it comes up later on. So that is called a matrix. That's called a matrix polynomial of A. Now this example here I'm going to leave for you guys to do on your own. That's very straightforward. You pretty much just plug the matrix. You basically just plug the matrix A into that polynomial, so you pretty much get the polynomial, or the matrix polynomial is simply going to be, it's going to be this matrix here that you multiply with itself. Okay, and to that you're going to add twice the matrix 1, 1, 1, 1, and to that you're going to add 1 times the identity matrix, which is 1, 0, 0, 1. And then you pretty much go and work that, this whole matrix expression out. Okay, so we know how to add matrices, we know how to add and subtract scalar multiples of matrices, so I'm going to leave that for you guys to do on your own. Right, so next up, as we get to the end of this section, is just basically a theorem on the properties of the transpose. So if A and B are matrices whose sizes are such that the indicated operation can be performed, if we take A and B to be matrices and we let K be a scalar, then A's transposes transposes A. Now, I already looked at a proof of this in the previous tutorial, so I'm not going to look at that. And then it seems the transpose function, it distributes over a sum between two matrices. So the transpose of the sum is the sum of the transposes. Okay, and if you take a scalar multiple of a matrix and you take the transpose, then the transpose has no effect on the scalar, and it just distributes into the bracket, and it works on the matrix itself. And then we have something that came from a previous tutorial, and that is that if you take the product between two matrices and you take the transpose, then in fact it is the product of the transposes, but in reverse order. And remember, previously we were asked to show whether this is true or false. Is it true or false that AB's transpose is A transpose B's transpose? Now, we worked that out and we showed that that is in fact not generally true. However, you can get an equality there if you do this. You switch the two around like that. Okay, so we will prove that one, and we will also just look at number 2. Right, so if we look at the A plus B's transpose, and we look at the entry in the ith row and the jth column of that matrix. If we look at the matrix A plus B, and if we look at the ith column of that matrix, and if we look at the jth row of that matrix, right, then if we take the transpose of A plus B, okay, then the ith row or the ith column of A plus B becomes the ith row of A plus B's transpose, and the jth row of A plus B becomes the jth column of A plus B's transpose, which is that there. And that entry there is basically the entry in the jth row of A plus the entry in the jth row of B and the ith column of B. Okay, so that is going to be the entry in the ith row and the jth column of A plus B's transpose. Okay, and that's easy now to go and look at that. The I comes basically it comes from the ith row and the jth column of A's transpose, and BJI comes from the ith row and the jth column of B's transpose, and that is basically A's transpose plus B's transpose, the entry in the ith row and the jth column of that matrix there. Okay, so basically we've got equality between A plus B's transpose and A transpose plus B's transpose.